Imagine yourself standing on a Martian beach 3.6 billion years ago. The crimson sky glows above, reflecting on dark waters stretching into the horizon. Gentle waves lap against your feet, and for a fleeting moment, it feels strangely familiar. Yet when you look up, two moons, Phobos and Deimos, hang in the twilight sky. The scene could almost be earthly, but every detail reminds you that this is another world. Mars, now a barren and frozen desert, may once have been a blue planet. Vast oceans may have covered its surface, shaping landscapes much like our own seas do today. Could this vision be reality? For decades, scientists have debated whether Mars once hosted oceans. Early satellite images hinted at coastlines, but their low resolution left room for doubt. To some, the patterns looked like beaches. To others, they were illusions of geology and erosion. The controversy dragged on for years. What we do know for certain is that water once flowed on Mars. Meteorites, minerals, and valleys carved into the terrain all point to its presence. But how much water existed and whether it was enough to form oceans remains a central question. While some researchers argue for vast seas rivaling Earth's, others insist the water was limited to rivers and lakes. The disagreement stems from the difficulty of interpreting data collected from millions of kilometers away. Without direct sampling, certainty has been elusive. In recent years, however, something changed. New missions equipped with powerful instruments began probing deeper, not only mapping the surface, but also peering underground. Their discoveries have reignited the debate with stronger, more convincing evidence. Among these missions, China's Tianwen-1 and its rover Zhurong stand out. For the first time, instruments directly examined a region suspected of being an ancient ocean basin. The results surprised even the most skeptical scientists. When combined with older findings, these new insights form a much clearer picture. No longer just speculation, the evidence for Martian oceans is growing stronger and more difficult to dismiss. Mars may have once been far more Earth-like than we ever imagined. In this journey, we will explore the key discoveries that changed how we see the red planet. From crystals trapped in meteorites to layers of hidden ice, each piece of evidence brings us closer to the truth. So get ready, because what follows are the 10 most compelling evidences that Mars was once home to vast oceans, and perhaps, just maybe, conditions suitable for life. The origin of the ocean. Hypothesis. The idea that Mars once had oceans is not new. As early as the 19th century, astronomers speculated about canals on the Martian surface. Some even imagined intelligent civilizations building waterways across the planet. Although these ideas were later disproven, they planted the seed for future scientific inquiry. Decades later, space probes brought back the first close-up images of Mars. The planet, long thought to be a barren desert, revealed valleys, depressions, and features that resembled coastlines. Some scientists proposed that these were remnants of ancient seas. The possibility was both thrilling and controversial. The debate quickly intensified. For every researcher convinced of Martian oceans, another dismissed the idea as misinterpretation. To skeptics, the supposed coastlines were nothing more than volcanic formations, tectonic fractures, or illusions caused by low-resolution images. Satellite technology of the time added to the challenge. The images were grainy, and many features were difficult to interpret with confidence. What some saw as deltas and beaches, others viewed as random geological patterns. The lack of clarity kept the theory in limbo. Still, the question refused to die. Mars held too many mysteries to ignore, and new missions were launched to probe its secrets. With each wave of exploration, the instruments grew more sophisticated, and the quality of the data improved dramatically. As higher resolution cameras and sensors revealed greater detail, more features resembling river valleys, floodplains, and possible shorelines were identified. These findings reignited the theory, drawing in both supporters and skeptics once again. Yet, without direct ground evidence, the argument remained unresolved. The biggest limitation was the lack of in situ data. Until recently, no rover had explored regions thought to be ancient ocean basins. Without boots or wheels on the ground, every interpretation was speculative, no matter how convincing the images appeared. That changed when China launched its Tianwen-1 mission. For the first time, A rover, Zhurong, was sent specifically to explore Utopia Planitia, a region long suspected of harboring evidence of an ancient ocean. This marked a turning point in the search for Martian seas. By studying the terrain both at the surface and below, the mission gathered unprecedented data. It provided scientists with new layers of evidence that went far beyond orbital speculation. For the first time, researchers could compare surface features with underground structures. Taken together, these observations strengthened the case for Martian oceans like never before. What was once a controversial hypothesis is now backed by stronger data, pushing us closer to the possibility that Mars once had vast Earth-like seas. Evidence 1. Meteorites with aqueous crystals. One of the earliest and most compelling pieces of evidence for water on Mars did not come from the planet itself, but from meteorites that landed on Earth. These rocks, ejected from Mars by ancient impacts, carried with them secrets locked inside their mineral structures. When studied under powerful microscopes, scientists discovered crystals that could only have formed in the presence of liquid water. These crystals act as natural time capsules, preserving conditions from billions of years ago. Dating methods revealed they were about 4.45 billion years old, meaning Mars hosted water very early in its history. This pushes the timeline of habitability back to the planet's formative years, when it was still geologically active. The formation of these crystals is impossible without liquid water. They require mineral-rich fluids to seep through rock and solidify into specific patterns. Their very existence proves that water once moved freely within the Martian crust, altering its chemistry and geology in profound ways. What makes this evidence especially powerful is that it was obtained on Earth, where scientists have access to the most advanced laboratory techniques. Unlike satellite images, which leave room for interpretation, these crystals were analyzed directly, reducing uncertainty and speculation. The minerals found inside the meteorites bear a striking resemblance to those formed in water-rich environments on Earth. This similarity reinforces the idea that planetary processes involving water are not unique to Earth but occurred on Mars as well. Such parallels suggest that both worlds may have shared a watery beginning. Even more intriguing, some of the crystals contain microscopic fluid inclusions, tiny bubbles of liquid trapped for billions of years. These preserved traces of Martian water provide a direct chemical fingerprint of the planet's wetter past, allowing scientists to study its composition in extraordinary detail. The presence of such minerals also hints at environments that may have been hospitable to life. Where liquid water persists, the possibility of microbial ecosystems cannot be ignored. Even if no life ever developed, the conditions would have been suitable for it to emerge. These meteorites also form part of a broader puzzle. By themselves, they demonstrate the presence of water, but when combined with other discoveries, they create a more cohesive narrative. Each piece of evidence strengthens the case for Mars as a once habitable world. It is important to remember that these meteorites traveled millions of kilometers through space before landing on Earth. Yet, despite their incredible journey, they preserved intact signs of Mars' ancient environment. They are fragments of history delivered directly into our hands. Thus, meteorites containing aqueous crystals represent the first direct, tangible proof that Mars once had water. They provide undeniable geological testimony that the red planet was not always dry and desolate, but a world shaped and transformed by liquid water. Evidence 2. Ferrihydrite in Martian dust. Another compelling clue for the presence of water on Mars comes from its dust, which blankets much of the planet's surface. Analyses conducted by orbiters and rovers revealed ferrihydrite, a mineral that only forms when water interacts with iron. Its discovery points directly to a watery past and ongoing cycles of hydration and desiccation. Ferrihydrite is not a stable mineral. On Earth, it transforms quickly into other iron oxides unless water is repeatedly present. Finding it on Mars suggests that the planet experienced multiple wet periods throughout its history. This means water was not a one-time occurrence, but a recurring force in shaping the Martian surface. The presence of ferrihydrite expands the timeline of water activity on Mars. It shows that liquid water was not limited to the planet's earliest days, but reappeared later in different cycles. This evidence suggests a planet that repeatedly flirted with habitability over billions of years. Ferrihydrite also reveals details about the geochemistry of Mars. Its formation indicates that fluids percolated through dust and rocks, altering their chemical structures. This means that Mars once had active water-rock interactions, processes crucial for sustaining potential microbial ecosystems. What makes this finding especially valuable is its connection to other evidence. Regions rich in ferrihydrite often overlap with dried riverbeds, deltas, and mineral deposits associated with water. Together, these features paint a consistent picture of Mars as a once wet and geologically active planet. Each new discovery adds another piece to the puzzle, but ferrihydrite plays a unique role. It provides a chemical signature of water, unlike river valleys that can sometimes be misinterpreted. Minerals do not lie. If ferrihydrite exists, water was undeniably involved. This evidence also undermined long-standing skepticism. Some researchers argued that many Martian features could be explained without invoking water. But ferrihydrite's presence is irrefutable. It requires water for its very existence, leaving no room for alternative explanations. Beyond proving water's presence, ferrihydrite tells us something about the climate of ancient Mars. Its existence suggests a world that went through phases of humidity and drying, much like Earth's deserts today. Such cycles could have fostered environments ideal for prebiotic chemistry. Ferrihydrite may also be a valuable target for future missions. If studied closely, it could reveal trapped chemical information about Mars water, including its pH, salinity, and possible traces of organic molecules. Each grain of dust could be a tiny archive of Mars' past. Thus, the discovery of ferrihydrite in Martian dust provides another solid line of evidence. It proves that water not only existed, but played an active and repeated role in shaping the planet's surface, making Mars a far more dynamic world than we see today. Evidence 3. Ancient riverbeds and channels. One of the most striking visual proofs of water on Mars comes from the vast networks of valleys and channels carved across its surface. Orbital images reveal winding paths that stretch for hundreds of kilometers, resembling the dry riverbeds of Earth. These patterns are almost impossible to explain without flowing water. Water erosion leaves distinct marks on landscapes. The branching structures, the meandering curves, and the fan-shaped deltas seen in Martian valleys all align with processes shaped by rivers. Wind alone could never reproduce such complexity, and tectonic activity lacks the fluid dynamics required to form them. In several regions, scientists identified features that look like deltas, where rivers once emptied into lakes or seas. Such structures require persistent and large volumes of water flowing over extended periods of time. They indicate not just brief flooding events, but sustained hydrological activity. The scale of these channels varies greatly. Some appear as narrow stream beds, while others are enormous valleys spanning hundreds of kilometers wide. This range mirrors the diversity of Earth's river systems, from small creeks to mighty waterways like the Amazon. Many channels terminate in depressions that may have been ancient lakes or even ocean basins. This direct link between rivers and potential standing bodies of water strengthens the argument that Mars once had a global water cycle. Rivers carried sediments downstream just as they do on Earth today. The evidence is reinforced by erosion patterns on crater walls and mountainsides. These streaks suggest that rainfall or melting snow once flowed downhill, carving paths into the landscape. It paints the picture of a Mars that once experienced precipitation and active weather systems. What makes this evidence particularly strong is its global distribution. These channels are not isolated to a single region, but found across the planet. This indicates that water activity was widespread, shaping Mars on a planetary scale rather than in localized pockets. Skeptics once argued that massive floods could explain these features without invoking long-lasting rivers. However, the diversity of channel types and their branching networks suggest continuous flow, not one-time cataclysmic events. The data points to a stable hydrological past. These riverbeds remain as silent witnesses of a time when Mars was alive with water. Though the rivers are long gone, their carved paths endure, etching into the planet's surface a story of abundance and change. Each valley is a relic of a vanished climate. Taken together, these ancient channels provide some of the clearest and most visible evidence of Mars' watery past. They demonstrate that liquid water was not only present, but abundant and dynamic, shaping the surface much like rivers have shaped Earth for eons. Evidence 4. Polar ice caps. Another undeniable clue to Mars' watery history lies in its immense polar ice caps. These frozen reservoirs, composed primarily of water ice with layers of carbon dioxide frost, cover regions so vast they rival the size of the continental United States. They are among the planet's most dramatic reminders of its aqueous past. Like Earth's polar regions, Mars' ice caps expand and contract with the seasons. This cyclical behavior shows that the planet still has an active climate system capable of redistributing water over time. The seasonal melting and freezing suggests that water is still playing a role in Martian processes today. Scientists estimate that if all of Mars's polar ice melted, the resulting water could cover the planet in a global ocean several meters deep. This staggering volume highlights just how much water remains locked away, preserved for billions of years under frigid conditions. The layered structure of the ice caps is also significant. Each layer represents a chapter in Mars's climate history, recording cycles of dust, ice, and atmospheric changes. Like tree rings on Earth, these layers act as an archive, preserving a timeline of planetary evolution. Beneath the surface, radar instruments have detected signs of subglacial lakes. These hidden bodies of water could remain liquid due to pressure from the overlying ice and residual geothermal heat. Such environments are potential havens for microbial life, shielded from harsh surface conditions. The polar regions also provide insights into Mars's past habitability. If life ever existed there, the ice could have preserved it, protecting organic material from radiation and oxidation. These icy vaults may hold biological secrets waiting to be uncovered by future missions. Beyond science, the polar ice caps are crucial for exploration. Water is a vital resource for sustaining human missions, providing drinking water, oxygen, and even rocket fuel through electrolysis. Colonies on Mars will likely depend on these reserves to survive and thrive. The existence of such enormous quantities of ice challenges the idea that Mars was ever completely dry. Even after losing much of its atmosphere and liquid water, the planet retained vast frozen reserves, underscoring its potential for once having oceans. The ice also supports models suggesting Mars once had a thicker atmosphere. For such large volumes to exist, conditions must have allowed water to accumulate, freeze, and remain stable over geological timescales. This ties directly into broader theories of Martian climate change. In short, the polar ice caps are not just frozen landscapes, they are monuments to a wetter Mars, preserving evidence of a time when water was far more abundant. Their presence provides a powerful argument that oceans once spread across the red planet. Evidence 5. Coastal sediments. Detected by Zhurong, China's Tianwen-1 mission, marked a milestone in the exploration of Mars. With its rover Zhurong, China became the second nation to land and operate successfully on the red planet. The chosen landing site was Utopia Planitia, a region long suspected to have once been an ancient ocean basin. The most remarkable tool aboard Zhurong was its ground-penetrating radar. This instrument allowed scientists to peer beneath the surface, mapping subsurface structures up to 35 meters deep. What they found astonished researchers: layers of material consistent with coastal sediment deposits. These buried layers were not random or chaotic. Instead, they revealed a clear pattern of stratification resembling beach formations on Earth. When compared to terrestrial analogs, the closest match was found in the Bay of Bengal, one of Earth's largest coastal sedimentary systems. Such patterns suggest that Mars once had dynamic shorelines shaped by waves and tides. The layering points to a process of sediment deposition over long periods, requiring a stable body of water like an ocean. This was the first direct evidence collected in situ of possible Martian coastlines. Before Zhurong, evidence of oceans came primarily from orbiters analyzing surface images. While valuable, these were often open to multiple interpretations. Zhurong's subsurface radar data provided the strongest support yet, moving the theory from speculation to stronger empirical ground. The scale of these sediments was equally impressive. They extended for over 1.3 kilometers, showing that they were not localized or accidental formations. Only processes involving large bodies of water could explain such widespread layering beneath the Martian surface. What makes this discovery even more powerful is the preservation of these structures underground. Shielded from erosion and surface weathering, they remain intact, offering a pristine record of ancient Martian hydrology. This opens opportunities for future missions to study them in greater detail. These findings also rule out the idea of transient lakes or floods. The sedimentary patterns indicate sustained coastal activity, not short-lived water events. They point to an environment that endured long enough for complex layering to build up. In reconstructing Mars's ancient geography, these sediments imply that Utopia Planitia was once filled with water. Vast beaches may have stretched across its borders, creating a landscape not unlike coastal regions on Earth. This reshapes how we imagine the Martian past. Thus, the coastal sediments uncovered by Zhurong stand as one of the strongest recent pieces of evidence for Martian oceans. They bridge the gap between orbital imagery and physical data, strengthening the case for a Mars that was once blue as well as red. Evidence 6. Uniform inclinations of sediments. One of the most striking findings from Zhurong's radar scans was the consistent angle of the buried layers. In total, scientists identified 76 geological reflectors beneath Utopia Planitia. Remarkably, all of them sloped in the same direction, with inclinations ranging from 6 degrees to 20 degrees. On Earth, this type of uniform slope is a hallmark of coastal environments. Beaches naturally form inclined layers as waves deposit sediment along a gentle gradient. Over time, these layers become preserved in the geological record, providing clear evidence of ancient shorelines. If the formations were caused by wind, like dunes, the inclinations would vary in multiple directions. Similarly, volcanic flows would produce irregular and chaotic structures, not a consistent slope. The uniformity observed in Mars's subsurface ruled out these explanations. The data strongly suggests that these were coastal deposits shaped by waves and tides. The repeated angles reflect a stable, long-lasting process, similar to what we see along terrestrial shorelines today. It indicates that Mars once had an active coastal system. This discovery is powerful because it provides a measurable physical characteristic. Unlike visual interpretations from satellite imagery, the angles recorded by radar leave little room for doubt. They represent a geological signature directly tied to water dynamics. The extent of these inclined layers adds weight to the argument. Stretching over more than a kilometer, they show that the process was not local or temporary. Only a vast body of water, such as an ocean, could produce such widespread and uniform sedimentary inclinations. Comparisons with Earth further reinforce the finding. Scientists highlighted the Bay of Bengal as an almost perfect analog, where similar slopes exist due to constant coastal wave activity. The resemblance is so strong that it is difficult to attribute it to coincidence. Beyond geology, these sediments may hold even more secrets. Inclined coastal deposits are excellent at trapping organic material and chemical signatures. If Mars once supported life, traces could still be preserved in these ancient beach layers, waiting to be discovered. This evidence also ties neatly into the broader puzzle. Combined with meteorites, dust minerals, riverbeds, and ice caps, the uniform slopes add another piece to the growing case for Martian oceans. Together, they tell a coherent story of a wetter world. In summary, the consistent inclinations of Martian sediments provide one of the clearest indicators of ancient shorelines. They are geological fingerprints left by waves and tides, strengthening the case that Mars was once home to vast and dynamic oceans. Evidence 7. Comparison with the Bay of Bengal. One of the most fascinating aspects of the Zhurong findings is how closely they resemble formations on Earth. When scientists analyzed the inclined layers detected beneath Utopia Planitia, they immediately drew comparisons to coastal sediments on our own planet. The closest and most striking match was found in the Bay of Bengal. The Bay of Bengal is home to extensive beaches and vast deposits of sediments shaped by waves, tides, and currents. Over millions of years, these processes created patterns of layering remarkably similar to those now seen on Mars. The parallel suggests that the same natural forces were at work. This comparison is crucial because it provides a tangible model. On Earth, we understand exactly how such formations develop. When nearly identical structures are identified on Mars, the simplest explanation is that they were formed by the same mechanism, the action of water. The sedimentary patterns in the Bay of Bengal are built by the steady deposition of material in a coastal environment. The slopes and stratification align with those uncovered by Zhurong's radar scans. This makes the Martian layers not just coincidental, but direct analogs of Earth's beaches. By using Earth as a reference, scientists gain confidence in their interpretation. While Mars has unique geology, certain patterns are universal. Water leaves behind distinct signatures, and these have now been detected on both planets, strengthening the case for ancient Martian oceans. The resemblance also implies that Mars's coastlines were not fleeting. Like the Bay of Bengal, they likely developed over long periods, with steady accumulation of sediments. This further rules out the idea of short-term flooding or brief water events. Such comparisons have helped sway even skeptical researchers. When evidence on Mars looks almost identical to well-understood Earth formations, it becomes increasingly difficult to dismiss. The parallels give weight and credibility to the ocean hypothesis. Moreover, this opens new avenues for exploration. If Martian coastlines functioned like Earth's, they may also have preserved organic molecules or other biosignatures within their sediments. Ancient Martian beaches could be prime targets in the search for past life. By studying Earth's coastal systems, we can also predict what future missions might find on Mars. Understanding sedimentation patterns here helps scientists design better instruments and strategies to investigate similar deposits there. In conclusion, the comparison with the Bay of Bengal does more than highlight similarities. It acts as a bridge between Earth and Mars, showing that processes shaping our oceans also sculpted alien shores billions of years ago. Evidence 8. Possible tides from Phobos tides are one of the most recognizable signs of ocean activity on Earth, caused by the gravitational pull of the moon. Mars, although smaller and drier today, has two moons, Phobos and Deimos. Phobos, in particular, orbits very close to the Martian surface, making it a candidate for generating tidal effects in ancient Martian oceans. Phobos is only about 22 kilometers wide, much smaller than Earth's moon. However, its proximity to Mars gives it a strong gravitational influence. If oceans existed, they would have likely experienced tidal shifts, with waters rising and falling in response to Phobos' orbit. The presence of tides would mean that Martian oceans were not static bodies of water. Instead, they would have been dynamic systems, with coastlines shaped by rhythmic cycles of movement. This adds another layer of realism to the idea of oceans on the red planet. Tides also play a critical role in shaping sediments. The repeated motion of water can create inclined layers and distribute material across shorelines. This aligns perfectly with the patterns of sediment deposition uncovered by the Zhurong rover. On Earth, tidal zones are rich in chemical activity. They create gradients of salinity, temperature, and energy that promote the formation of complex organic molecules. If similar tidal processes occurred on Mars, they could have provided favorable conditions for the emergence of life. Even though Phobos is much smaller than our moon, its nearness amplifies its gravitational effect. The tidal forces it exerted on Mars's oceans may have been sufficient to create noticeable shifts, enough to influence coastal dynamics and sediment layering. This hypothesis also provides a stronger explanation for the uniform inclinations seen in Utopia Planitia. The constant push and pull of tides would have contributed to the creation of stable, directional slopes preserved beneath the Martian surface. The idea of Martian tides further strengthens the ocean theory. It shows that Mars's waters were not just passive or temporary, but part of a dynamic system interacting with its moons. This makes the ancient environment feel even more Earth-like. If confirmed, this would mean that Phobos shaped more than just the Martian sky. It actively influenced its oceans. Such a connection highlights how celestial mechanics can play a direct role in shaping planetary habitability. In summary, the possible tidal effects of Phobos offer yet another piece of evidence for Martian oceans. They suggest a world where water moved, shifted, and transformed under gravitational influence, leaving behind patterns still visible billions of years later. Evidence 9. Ruling out alternatives. When Zhurong detected subsurface inclined layers in Utopia Planitia, scientists knew they had to test every possible explanation. Jumping straight to the ocean hypothesis without considering alternatives would be premature. Thus, they carefully evaluated other geological processes. The first possibility was sand dunes shaped by wind. Mars is a windy planet, and dunes are common across its deserts. However, dunes create slopes pointing in multiple directions due to shifting wind patterns. The uniform angles seen underground did not match this behavior. Another candidate was lava flows. Mars has a rich volcanic history, with massive eruptions shaping much of its surface. Lava can solidify into layers, but these are irregular and chaotic, not neatly aligned in one direction. Again, the data did not fit this scenario. Asteroid impacts were also considered. Large impacts can create fractured layers and chaotic structures. Yet, these lack the consistent slopes and ordered geometry observed in the Zhurong radar scans. The impact explanation was quickly ruled out as incompatible. In contrast, coastal processes explain the evidence perfectly. Waves and tides naturally deposit sediments in inclined layers, all sloping toward the ocean. This process creates precisely the kind of uniformity detected beneath Utopia planitia. To strengthen their case, researchers compared the Martian data with terrestrial analogs. When placed side by side with coastal formations on Earth, the similarities were striking. The Martian layers matched beaches, not dunes, lava flows, or impact deposits. This comparative approach left little room for doubt. By systematically eliminating alternatives, the ocean explanation became the only consistent one. Science often advances by exclusion, and here, the process pointed directly to ancient seas. The regularity of the inclined layers also suggested long-term stability. Random events like volcanic eruptions or asteroid impacts cannot create such order over kilometers. Only sustained coastal activity could generate these patterns over extended timescales. For skeptics, this process of elimination was critical. Instead of relying on imagination, the data forced a logical conclusion. When every other hypothesis failed, the idea of Martian oceans remained standing as the most plausible. Thus, evidence 9 lies not only in what was found, but also in what was disproven. By ruling out wind, lava, and impacts, scientists strengthened the argument that Mars once had coastlines shaped by waves and tides, just like Earth's shores today. Evidence 10. Subsurface ice in Utopia. Planitia. One of the most remarkable discoveries about Mars came in 2016, when NASA scientists using radar detected vast underground ice deposits in Utopia planitia. This region, later explored by Zhurong, turned out to contain a staggering volume of frozen water hidden just below the surface. The estimated amount of ice rivals the volume of Lake Superior, the largest of North America's Great Lakes. With roughly 1,100 cubic kilometers of frozen water, this single reservoir represents one of the largest caches of Martian water ever identified. Its preservation underground is critical. On Mars, exposed water ice quickly sublimates into vapor under thin atmospheric pressure. But buried beneath layers of soil and dust, the ice remains stable, shielded from the harsh radiation and extreme temperature swings at the surface. This finding strongly supports the theory that Utopia planitia was once an ocean basin. When the water disappeared from the surface, much of it may have seeped underground, freezing in place. What remains today is a frozen relic of a once vast and dynamic sea. For future exploration, this discovery has enormous implications. Ice can be melted for drinking water, split into oxygen for breathing, and hydrogen for fuel. Any long-term human mission to Mars will depend heavily on resources like these to survive. Scientifically, the ice is just as valuable. By drilling into these deposits, future missions could analyze chemical traces preserved inside. These could reveal the composition of ancient Martian oceans and perhaps even capture microscopic evidence of past microbial life. The scale of this ice also reshapes our understanding of Mars' climate history. Such a massive reservoir could not exist without significant water activity in the past. It implies that Mars once had the right conditions to store, circulate, and preserve large quantities of water. The ice also highlights how Mars has never been completely dry. Even today, beneath its dusty surface, it hides enormous reserves of frozen water. This continuity suggests a planet that has always maintained a connection to its watery past. When combined with the evidence of rivers, deltas, and coastal sediments, the Utopia planitia ice completes the picture. It shows that oceans once existed and left behind vast frozen remnants, still detectable billions of years later. Thus, subsurface ice in Utopia planitia stands as one of the strongest proofs of all. It is a frozen monument to Mars's ancient oceans, bridging the past and the future, evidence of what once was, and a resource for what is yet to come. The paradox of the young and faint sun. Even with mounting evidence of oceans on Mars, one great mystery remains. How could liquid water have existed under the weak sunlight of billions of years ago? About 3.5 billion years in the past, the sun was roughly 25% dimmer than it is today. Under such conditions, Mars should have been frozen solid. This puzzle is known as the faint young sun paradox. Climate models suggest that with such little solar energy, Mars's surface temperatures would have stayed well below freezing. Yet geological evidence clearly shows rivers, lakes, and even possible oceans. The contradiction remains unsolved. One proposed solution is that Mars once had a much thicker atmosphere. Carbon dioxide and water vapor could have created a powerful greenhouse effect, trapping enough heat to allow liquid water to persist. However, models show that CO2 and water vapor alone would not have been sufficient. Another theory suggests the presence of additional greenhouse gases such as methane, hydrogen, or ammonia. These could have provided the extra warming needed. The problem is that such gases are unstable and would not remain in the atmosphere for millions of years without constant replenishment. A different possibility is that Mars was not continuously warm, but only episodically. Large volcanic eruptions or asteroid impacts could have released bursts of heat and greenhouse gases, creating temporary warm periods where ice melted, rivers flowed, and erosion occurred. This intermittent warming could explain localized valleys and lakes, but it struggles to account for evidence of long-lasting oceans. To sustain coastlines and sedimentary layering, Mars would have needed stable water for extended periods, not just brief episodes. A third scenario envisions Mars as an icy world most of the time, with oceans and lakes hidden beneath thick sheets of ice. Periodic warming events, orbital shifts, or geothermal activity could have melted the ice, allowing temporary surface water. This could explain the mix of glacial and fluvial features. The paradox highlights how complex and puzzling Mars' climate history is. None of the proposed explanations fully resolve the mystery. Scientists continue to test models, but reconciling the presence of oceans with a faint sun remains one of planetary science's biggest challenges. Solving this paradox is not just about Mars, it also has implications for Earth. Our planet, too, experienced a faint young sun, yet it remained warm enough for oceans and life to flourish. Understanding how could reveal universal principles of habitability. Thus, the faint young sun paradox stands as a central unanswered question. It reminds us that while the evidence for Martian oceans is strong, we still lack the complete picture of how they could have existed under such dim starlight. The fate of Mars' lost water. If Mars once had vast oceans, a critical question emerges. Where did all the water go? Today, the planet appears dry and desolate, with only polar ice caps and subsurface deposits. Yet billions of years ago, oceans may have covered entire regions. Understanding their disappearance is one of the great mysteries of planetary science. One explanation is atmospheric loss. Mars once had a much thicker atmosphere, capable of supporting liquid water on the surface. But without a strong magnetic field to shield it, solar winds stripped the atmosphere away. As pressure dropped, water evaporated and escaped into space. Another possibility is that much of the water seeped underground. Protected beneath layers of soil and rock, it froze into enormous reservoirs, such as those detected in Utopia planitia. These frozen stores remain preserved even today, hidden beneath the Martian surface. Some of the water may also be locked inside minerals. Certain rocks can absorb water molecules into their crystalline structures, effectively trapping them for billions of years. This mineral-bound water would be invisible on the surface, but still part of the planet's hidden reserves. Climate models suggest that Mars underwent gradual cooling. Oceans shrank into lakes, lakes became glaciers, and eventually most water ended up frozen at the poles or underground. The transformation from a blue world to a red desert was slow but relentless. There is also evidence that liquid water may still exist today in isolated locations. Radar studies near the South Pole suggest possible subsurface lakes kept liquid by pressure and geothermal heat. If confirmed, these would be prime targets in the search for life. The loss of water is also tied to Mars' lost magnetic field. Billions of years ago, the planet's magnetic dynamo shut down, leaving its atmosphere vulnerable. With no protection, particles from the sun stripped away gases, accelerating the drying of the planet. Even though much was lost, the fingerprints of water remain everywhere. Dry riverbeds, deltas, sedimentary layers, and buried ice all testify to a planet that once flowed with water. These features make it clear that Mars's watery past was real and extensive. For future human explorers, the fate of Mars's water is more than academic. If large reserves remain underground, they could provide the foundation for colonization, supplying drinking water, oxygen, and even rocket fuel. Mars's past may hold the key to its future. In the end, the question is not whether Mars had oceans, but how much of that water remains. Trapped in ice, minerals, or hidden lakes, the story of Mars' lost water is still unfolding. Solving it may finally reveal the full history of the red planet. The future of exploration. With so much evidence pointing to oceans on Mars, the next step is confirmation through direct analysis. Future missions aim to return Martian samples to Earth, where they can be studied with the most advanced technology available. These samples could finally settle the debate on Mars' watery past. NASA and ESA have been preparing the Mars Sample Return Program, originally scheduled for the early 2030s. However, technical challenges and budget constraints have already delayed its timeline, and some estimates now place its completion closer to 2040. The mission remains ambitious but uncertain. Meanwhile, China has its own bold plans. Following the success of Tianwen-1 and Zhurong, the Chinese Space Agency announced future missions to bring back Martian soil and rock. They even envision sending humans to Mars by the 2030s, intensifying the global race to explore the red planet. These missions are critical because they will allow scientists to study Martian sediments and ice directly. Instruments on Earth are far more powerful than those on rovers. With physical samples, researchers can search for isotopes, organic molecules, and even microfossils that might confirm life once existed. Private companies are also entering the arena. SpaceX and other ventures dream of building colonies on Mars. To succeed, they will need to rely heavily on in-situ resources like water and ice. This makes the study of ancient oceans not just a scientific pursuit, but a practical necessity. Every new mission brings us closer to answering fundamental questions. Did Mars truly host oceans? Did life ever emerge in those coastal environments? And if it did, can traces of it still be found buried beneath the surface? Each launch is a step toward these answers. Even if life is never discovered, confirming the existence of Martian oceans would still be revolutionary. It would prove that habitable conditions are not rare in the universe, but may arise wherever water and the right chemistry meet. Mars would serve as a cosmic reminder of that possibility. Exploration also forces us to reflect on Earth's future. By studying why Mars lost its oceans, we gain insight into planetary evolution and climate change. Could our own world face a similar fate billions of years from now? Mars may hold the clues. What is certain is that Mars will remain a top priority for decades to come. Each mission, whether governmental or private, adds to the mosaic of knowledge. Together, they will eventually complete the story of a planet that was once far more alive than it appears today. Thus, the future of exploration is not only about solving scientific mysteries, but also about preparing for humanity's destiny among the stars. Mars, with its hidden oceans and frozen relics, may be the first stepping stone into a broader cosmic journey. In summary, the discoveries on Mars reveal a planet far more complex than its current frozen desert suggests. From meteorites and riverbeds to polar ice and buried shorelines, the evidence builds a compelling case for ancient oceans. Questions remain about the sun's faint light, the fate of lost water, and whether life once thrived there. Yet each mission brings us closer to the truth. Until we hold Martian samples in our hands, the mystery of Mars's oceans will continue to inspire our search for life beyond Earth.